Let's study the displacement of a conical and cylindrical tank. The model of the conical tank. We can observe the radius, the height, and the angle beta. The tangent of beta is the radius over the height. Therefore, r is h, and the tangent is theta. We have the formula, the equation of the conical tank. Knowing that r is h tangent of beta, replacing, we have this expression. This is the final expression for the volume of the conical tank. We can consider beta constant. Therefore, the derivative of the volume in relation to the height will be 3h2 pi h2 tangent of beta superscript 2 over 3 that we already had. Cut 3 with 3, and we'll have pi h2 tangent of beta superscript 2. Applying the mass conservation equation, the mass will be equal to the volume of the tank. There is no mass at the entrance, so the mass of the exit will be equal to the mass accumulation in the system. Remembering that mass over volume is density. Substituting the equations, and knowing that the velocity of the tube times the density and area of the tube will be equal to d rho v over dt. Substituting this equation here, we would have this. Let's cut the rho with rho, and we'll have this expression here. The expression of the velocity at the exit of a tank is given by this equation here. Deduction of equations from the balance of energy conservation from previous lessons. We know that the velocity at the exit of a tank is proportional to the height of the liquid. The square root of the liquid, 2gh. This is the area of the tube, that is, the transverse area of the exit, which is here. That's it. dV over dt. We know that the area of the tube is pi r superscript 2. dV over dt is the same as dVh over h over dt, because by cutting this h with this h we get dVh over dt. So if we can isolate dH over dt, like here, and knowing that dVh is deduced here, this dVh is here, substituting dVh here. In this expression, we get that dVh over dt is equal to 2gh pi r superscript 2 of the tube over the expression of dVh, which is here. And let's solve this in Octave or MATLAB numerically by Runge Kutta, plotting 1 liter of fixed water at angles of 30 degrees, 70 degrees, with 5 steps. We will also model the cylindrical tank for the effect of comparing the height of the tank. Here is the radius of the tank, and here is the radius of the tube. The same equation of mass balance, it will be easier, of mass conservation. Of, where v is the speed of exit of the tank, which is given by this expression here rho v, which is the mass, rho is constant, we will cut rho, it will be the base area times the height of the cylindrical tank. So, the expression we find will be this one, which is this one here. Now, what are we going to do? With the expression found of dH dt, we will solve, numerically, by Runge Kutta, in Octave or MATLAB, with the same height values of the cylindrical tank for 1 liter also, and make the comparison. Okay, let's go.
After the modeling, now let's contextualize the computational part. So we made this program. The tube radius leaving the cone is 0.5 centimeters. Then we pass to the metric data. We have this. Gravitational acceleration 9.81 m/s². The area at the exit of the cone tube will be this. The equation. This is the equation here. The equation dH to t, right? Of our modeling, dH to t, tangent, because this tangent here is in degree, right, in degree. Here is the same auxiliary function. This one auxiliary is the same function of this one for us to play in the equation of the leak. This one is the differential equation d beta dt, where d beta dt does not vary, so it is equal to 0, okay? And the other variable would be dv dt, which would be calculated, which would be the leak, which is exactly dh dt, which is here, right? dh/dt, which is here, times dv/dh of our formula. Ready, we calculated, made the program of differential equations. Now, to run this, we will vary the angle beta from 30 to 70, right? Here it will vary from 30 to 70, right, to a fixed volume of 1 liter in international system units, 1/10 to -3. The height is here. Due to this fixed volume, you just have to play in the cone volume equation. We have the height, and we will put this height here, and it is varying because beta varies from 30 to 70 here. Then, we will solve by the Runge-Kutta method. The Cone 3 program with a time varying from 0 to 20, height varying, beta varying, and it will plot 3D. I multiplied by me here for the answer to stay in liters, right? So running the program, we would have then what will happen with the cone and the same thing. Tougher, what will happen with the cylinder, right? The volume is 1 liter. The volume is fixed. The cylinder is 001. The internal radius of the tube of the exit of the cylinder is here. There is the area of the tube here. The differential equation of the modeling. Its auxiliary, dv, dh, the angle that does not vary, equal to 0, and here, the equation of the vase, dv, dt, which is the AUX, which is this AUX here, which is dh, dt times dv, dh, which is here, this, dv, dh, which is here, this y here, is corresponding to the beta, which is beta squared. Okay, now, just confirm here. It's all right, right? It's right. That's right, dv, dh. That's it. Let's save. So, we will get, then, these expressions. This figure, after running the program, we get this figure here, which is very interesting. And what do you notice? That the time, this part here, is due to what? To the cone. This here is the cone, so the cone emptying time for several angles, right? We will have several. If I insert a caption here, insert this caption here, right? This first blue curve here is due to the angle of 30 degrees, which increases and the time increases, so the cone emptying time is in the order of 2 to 4, right? 2 to 4, and the cylinder takes much longer. Look there, 14 seconds to 20 for the same heights, right? If we wanted to see this here, in relation to the emptying time, here is the height, here is the volume, right here for the tank 1, here the emptying time of 2 to 4 for the cone. Emptying time of 1 liter, right, in the cone, varying angles of 30, 35, and here for the cylinder, which will give a much longer emptying time for 1 liter also with the same radius of the cone, okay, the same radius in the base of the cone there will be the same, right? So that's it.